All right, welcome everyone. My name is Alec Shedelbower, and I'm a developer here at Wolfram Research. I work on the discrete computation team, and today I'm going to be talking about the latest in graphics and shaders. So a quick overview of today's talk. I'm going to start off with an introduction to rendering and go over what the process entails and how shaders fit into that. Then I'm going to switch over to shading models, which is when we perform different lighting calculations. After that, I'll go into our artistic shading. This is stuff like tune shading or hat shading, which try to create these stylized effects. Next up, I'm going to do physically based shading with material shading. This is how we get those more photorealistic results in a way that is more physically based than the artistic approaches. Lastly, I'm going to talk about some of our 2D shaders, including the new drop shadowing directive, which I think is pretty neat. And just a heads up, so feel free to ask any questions in the chat. I probably won't be able to answer them during the talk, but I'll leave some time at the end to try and go through them. Any questions I do not get to, I'll try to answer in the community posts that goes along with this stream. All right, with that said, let's go ahead and get started. So rendering, what is it? So rendering is a process of converting our representation of a 3D scene into a 2D image. Now, this image is made up of a grid of picture elements, or pixels for short. In order to render a scene, we have to determine the color of each of these pixels. This is a bit of a problem because there can easily be 1 million pixels in a scene for our image. So in order to kind of get that render, we have to find a color for all those pixels. Luckily for us, rendering is what's known as a heavily parallelized problem, where each pixel can be calculated independently. This lets us use specialized hardware like the GPU to run thousands of threads and pixel calculations at once. And with all of this, we're able to create a kind of real-time rendering where we can get up to 20 to 60 frames per second. Now, in order to render a scene, let's first discuss what a scene is. So a scene is our virtual environment that contains the models, lighting, and camera used for rendering. In a Wolfram language, we describe scenes using graphics 3D. So for example, here's a very simple scene. We have a sphere model, we have kind of this lighting preset, and a camera is defined for us to kind of rotate around our object. Now we can kind of go into more details about these 3 separate components. First up being the models. So the model is the surface geometry of visible objects in the scene. In Wolfram language, these models can be anything from our graphics primitives like cubes, spheres, or capsules to more general structures like a graphics complex or a mesh region. Models are almost always represented as triangle meshes during rendering, even the ones that look smooth. For example, our spheres and cylinders and such, when we go to render them, they all just become a kind of mesh of triangles. In addition to this kind of vertices and triangle data, we may also contain other data such as normals, colors, and texture coordinates for each vertex. We'll see some of that more later. All right, next up we have lighting. So light sources are required to illuminate the models in the scene so they're visible to the camera. Without lighting, we don't have our image. So for real-time rendering applications, we use these very simplified models of light in order to have faster computation times. So these 4 lights are known as analytical lights, and these are what are available in the Wolfram language in most real-time rendering applications. The first one here on the left is directional lighting. This is light that runs in parallel rays from a single direction. So this is useful for things like approximating the sun, which is so far away that by the time the light gets to us is basically parallel. Next up, we have point lights, which emanate from a single infinitesimal point in all directions. This is good for stuff like a light bulb in a room. Next up, we have the spotlight, which is essentially the same as a point light. The only difference being that instead of radiating in all directions, it radiates in a cone. And lastly, we have the ambient light. This one's a bit odd in that it has no position or direction. However, it kind of adds a default amount of lighting to all objects in our scene. This is used to kind of simulate global illumination, which is the process where when a light ray hits an object, it tends to keep bouncing around for a while before stopping. So this causes things that are not directly lit by a light source to still have some lighting on them and be visible. All right, so with those 4 lights, we can see they have kind of 4 corresponding symbols in the Wolfram language below. So in order to kind of specify these lights in our graphics 3D scene, we have a couple ways of doing it. So kind of the legacy way was to use the lighting option and pass these sort of list where we have the type of light and its parameters following it. However, we have recently added these new kind of light symbols. So now you can, per se, do a directional light here and pass in the parameters like so. The neat part about this new method is that we can also add these two kind of scene as a directive. For example, if we wanted to light this cube with a blue light and the sphere with a red light, but not light both objects with those lights, we can do so like we would any other kind of graphics directive. All right, flying out of the way, the last thing in our scene is the camera. So the camera determines where and how the models will be positioned in the final rendered image. The camera settings are specified with various view options in the graphics 3D. I pulled out some of the main ones here so we can kind of see what they do. So in this kind of interactive example, we have our scene on the left and the final output image on the right. So you'll notice that the camera forms this kind of pyramid shape with the top kind of sliced off. The shape is called the frustum, and it kind of determines what is visible in our scene. So only the things inside of this kind of truncated pyramid will be rendered to the final image. So kind of the first part that makes up this frustum is this kind of focal point, the viewpoint. So this is like where your eye or the camera would be in real life. So as we move this around, we can see we kind of change where we're looking from. By default, it will look towards the kind of center of our scene. That's why we're seeing it following this cube. Next up, we have the view angle, is also known as the field of view. This is basically how open the camera sensor would be, and is equivalent in real life to zooming in and out. You can kind of see it changes the narrowness of our pyramid. Next up, we have the view range. This determines the start and stopping cutoffs for our pyramid. So as we increase this near plane, we'll see it slice into our cube, and we no longer see that cube visible over here on the right. And we can do a similar thing if we bring our far plane too close, it'll kind of slice away the geometry as well. All right, and the last option we'll go over here is the view vertical, which just tells us which way is up in our final image. So we see here on this plane, we have this red line on the bottom of the image. And as we change our view vertical, we're going to kind of rotate our whole view frustum kind of along that view direction. All right, so that makes up the main aspects of our camera. And just keep in mind that this plane right here, or called the near plane, is going to be important coming up in the next slide. All right, so now we have the three components of our scene. We want to know how to actually render something to the screen. So we can do this by first imagining our image is embedded in the scene with all of its pixels on that near plane I just mentioned. We can then take the center of each pixel and draw a kind of ray from that to our viewpoint. So then we can kind of assign each of these pixels with that view direction. Now the light that would come from that pixel has to come through that ray and through that pixel center. So that's will determine the color of the pixel is the light that follows that kind of line. Now, since we assume light travels in straight lines for our rendering, this will mean that that light will have to come from a surface point that lies along that line from the viewpoint through the pixel center and then eventually intersecting with that geometry. Yeah, so now the question is, how do we determine what this final surface point is that corresponds to a certain pixel? There are two main ways of doing this. The first way is kind of the more intuitive, where we basically just flip that view direction and do a ray cast into our scene. If our ray intersects with any geometry, we know we've hit a surface. We can then know which pixels hit a surface and which ones do not. This method is, while intuitive, usually much more computationally intensive, and is usually saved for kind of offline renderers. For real-time renderers, we usually use something called rasterization, which is a little less intuitive, but much faster. So this method, we kind of do the opposite, whereas for raycasting, we kind of project our pixels onto the scene. Here we're going to project our scene geometry onto the pixels. So we do this using a kind of series of fine transformations that eventually kind of squish our geometry onto that plane. Once it's squished, we kind of take each triangle and then perform the actual rasterization on it, which is essentially just determining which pixels we should consider inside the triangle and which ones are outside. While we're doing this kind of rasterization, we can keep track of kind of the various centric coordinates for each of these points, and that lets us kind of easily interpolate values from the vertices to those pixels. mostly being the position, so we can know exactly where that surface point is. All right, so after all that, we know the surface position of our point. We know the view vector. We know the light vector, which for each light, we can calculate the direction of that incoming light. And then we can know the surface normal vector of that surface point. With this information, we can then calculate convincing 3D shading on our object. So kind of the most basic form of this, but also very effective, is this kind of diffuse Lambertian shading. So this basically calculates how much of the light reaches the surface based on the angle between the surface normal and the light vector. So we see here when they are basically aligned and parallel, it's at its brightest. But as we increase that angle going on the side of the sphere, it's going to get darker and darker. The formula for calculating this is simply the dot product between that surface normal and the light vector, which is also equivalent to the cosine of their angle between those two vectors. And the reason it is that value, we kind of think of if we have our surface here and we're to imagine a very infinitesimally small patch, and then all the light that reaches perpendicularly and hits that patch. So we imagine this has like full illumination. As we increase the kind of angle of incidence of that light, we're going to see this patch slowly start to kind of stretch out over the entire surface. Now, why the area of this patch will kind of increase proportional to the secant of that angle, the actual kind of remaining light in our original patch will be proportional to cosine of our angle. So that's kind of justification for why this effect occurs, why we have that fall off as the angle increases. All right, and then going on from just plain diffuse lighting, we have one of the kind of canonical rendering reflectance models here called the PHONG reflectance model. This was developed way back in 1975, but is still used today. So this method kind of calculates 3 separate components of light that we then combine at the end for the final render. So the first component is what we just saw with that Lambertian diffuse. We then have a specular component, which captures kind of the small highlights on shiny objects. This occurs when the light reflects off the surface towards the viewer. And lastly, we have this ambient component, which is kind of just the default amount of light we want to add, just so nothing that is not fully lit isn't pitch black. Yeah, we add these all together and we get our nice PHONG reflection. Now in practice, there's a very similar version of this called the blend PHONG reflectance model. That is very similar, but slightly more computationally efficient. So that tends to be the default nowadays for these kind of more simple renders. All right, that's kind of basic of rendering there. Next up, I'm going to talk about shading models. So whereas kind of those lighting models I mentioned, they determine how much light is reflected from a surface point, the shading models determine when we perform those lighting calculations. And there are kind of 3 main types that have kind of iterated over time. The kind of original was per face, also known as flat shading. We had per vertex, also known as Garot shading. And lastly, we have per pixel, also known as PHONG shading. And side note, this PHONG shading is different than the PHONG reflectance model. They're both kind of released at the same time by the same person, so they kind of share the name. All right, we start with the first one there. We talk about our per face lighting. So this can be accomplished with the new flat shading symbol. So what this does is calculates a single face normal for every triangle, and we only use that normal when calculating the lighting. So this has the effect of kind of giving each polygon a single solid color. So that kind of reveals all the hidden polygons on these otherwise smooth objects. For example, this is the normal sphere, but with flat shading, we can kind of reveal all the quads that it's made of. And you can see what it normally looks like here. Next up, we have the Garot shading. This is per vertex lighting. This was kind of an attempt to improve that flat shading, where instead of doing one normal per face, we're going to do one normal per vertex. We will then calculate our lighting at each of those 3 vertices. And then when we have that final color, we'll just interpolate that color across the triangle, the same way we would do its position. So this works really well for simple kind of diffuse objects or objects with a lot of triangles in it. As you can see here, it looks pretty much indistinguishable from the default system shader, which I believe uses blend PHONG. However, it kind of breaks down when we get a kind of low polygonal models that have some specularity to them. For any basically sudden shift in like intensity of light across the polygon space, cannot be captured by this method because we only calculate light at the very corners of the triangle. So you can see here we have a specular highlight on this, but it only shows up when it happens to align with the vertice. When it aligns with the center of a triangle, it does not show at all. So to kind of combat this, we have the final shading method here. So this one is PHONG shading. It's kind of the standard technique for modern graphics, where instead of interpolating colors at each vertex, we interpolate their normals. So we can get a kind of interpolated normal at each pixel on the triangle. Once we have that, we can perform the full lighting calculation for each pixel that we see. So for our simple diffuse, it will appear very similar to the Garrod shading. However, when we go back to that kind of highly low poly model with that specular highlight, we see now it does correctly show the highlight as a nice round object, regardless of which direction or where it lands. And then one final note, while PHONG is higher fidelity than Garrod shading, there can still be used for Garrod in kind of very high performance situations. For example, the default system shader we have, it will use kind of PHONG shading by default, but as you rotate, it will switch over to that Garrod shading where it's per vertex instead of per pixel, as you can kind of see here as you rotate. All right, and that's those shading models. Next up, I'm going to be talking about these kind of artistic shaders we have, which try to focus not on realism, but a certain stylized effect. So here we have kind of a list of the ones we've added, where we have stuff like hand-drawn effects, kind of cell-shaded toon shading, something that's more kind of like a comic book halftone effect. And so all these methods are meant to kind of invoke a certain style and not necessarily be realistic. A fun fact is that these all actually use the same underlying shader, just with different parameters. And a shader is called a ramp shader. So a ramp shader is a flexible shader that can achieve many common artistic effects. It uses what's called a ramp lookup texture to control the exact color surface at different light levels. So it's essentially a blend PHONG shader with some extra post-processing at the end. So the kind of overall steps for doing it is it does the initial kind of blend PHONG lighting calculation to find the color of the surface. We'll then calculate the luminance of that color as a scalar between 0 and 1. We can then use that luminance as an index to index into our kind of ramp texture to find the final color. And kind of first take a look at this luminance and how that's calculated. So when we do that normal lighting calculation, we end up with the RGB color that has 3 channels. And we need a single kind of scalar value for a texture lookup. So we could just take the average of these 3 channels, and that would give us a decent approximation. However, it's generally better to use something called luminance, which measures the perceived brightness of that color. I say perceived because humans, our eyes do not perceive each color as being the same brightness, regardless if they have like the same kind of power. For example, you often see green as much brighter than the equivalent blue or red color. In order to do this, instead of using a kind of uniform weighted average, we'll use a weighted sum of those 3 RGB channels, red, green, and blue. And here's kind of the weight we use for our shader. And then that will give us the final kind of grayscale value for how bright that pixel is. So here you can see kind of just a rainbow of colors and see if we just average them, what the kind of average brightness would be. And then we can see if we use its luminance, how the blue and red appear much darker than, say, the green and the yellow. And once we have that luminance, we can basically imagine this graph as kind of showing the distribution of light levels across our entire kind of final image. We can kind of map our ramp value to that 0 to 1 scale, and then we can kind of shade our object accordingly. So here we have on the right, it's this kind of yellow-green that transitions into a blue. And so the brightest stuff will be that yellow-green on the right here, and the darkest parts will be this dark blue. All right, now in terms of texture, typically ramp shaders use a 2D texture for their ramp that is 1 pixel high and then some numbers of pixels long. If you use a nice smooth kind of gradient texture like this, we get something like the classic coach shading here, which just goes, has a gradient from the dark to light kind of values of our render. However, we can achieve a different effect if we create some kind of very drastic sharp cutoffs here on our ramp texture. And this gives us kind of the famous tune shading, where we have these very kind of discrete sections of highlight, midtone, and the shading of the shadow. However, for our actual ramp we use in Wolfram language, we actually use a 3D texture ramp for this. So it's 1 by 1 by some number of pixels. This gives us more flexibility in that we can use full textures instead of just a single color. So this comes in handy for doing stuff like tonal art maps, which is where you can create a series of textures that you can blend between to go from a very kind of sparse light texture to a very dense dark texture. So for example, for our hand-drawn effects and even the halftone shading, we use a series of textures with increasing number of marks on them. And then we kind of create this 3D ramp texture here, where on the left, we see it has a very kind of bright and sparse texture, and we transition to the darker textures over here. And when we kind of apply this as our ramp, you can see that these highlight areas now have that very sparse, almost non-existent texture there. While as we go to a darker area, we see more and more lines kind of slowly fade in. Make it a little bigger to make it more obvious. Yes. And a similar effect happens with the stipple and halftone shading. Just a different kind of set of textures is used. All right, that sums up the kind of artistic shaders we have. So next up, I'm going to go into kind of the opposite, which is the physically based shading. So physically based shading is a shading method that attempts to model behavior of light in the real world. PBS is just one component of the kind of larger umbrella term physically based rendering, which deals with things beyond shading, such as lighting and camera definitions. However, for now, we're just focused on the shading aspect. So in Wolfram language, it's implemented as the material shading symbol. So we can see here, we can just add this symbol as a directive, give it a kind of preset material name, and we can see our nice kind of metallic render shown below. Material shading comes with a variety of kind of name material presets that you can just easily use and plug in to any of your scenes. We have various metals and some more kind of unique shape, unique materials over here. You can even define your own custom materials by specifying these properties manually. In one moment. All right, now in terms of how this kind of the theory behind all this, so there is a lot of like in-depth theory and calculation behind physically based shading, so much so that they're worth their own presentation, which I'll probably give at a future date. For today, I'll just go a kind of quick high-level overview of this. And if you are curious and want to read more about it, I also have this tutorial in our documentation that goes into depth about this theory and the actual implementation we use for material shading. Yeah, I want the kind of higher level aspect. So it all kind of starts with this reflectance equation. So kind of the goal of our shader is to solve this reflectance equation, which basically is just saying the kind of light that leaves a point on the surface of our object towards the viewer is going to be equal to the light emitted by the object and the light reflected off that object. Now, the light emitted can usually be ignored for most cases, as most of our objects do not kind of radiate light on their own. So we're going to focus on the reflected light here. So if you look at this reflected light, we'll see it it's kind of formulated as an integral over this hemisphere with these different kind of subfunctions here. So kind of a visual representation of this whole integral is shown by this diagram. So we have kind of our surface point here, P, we have our normal vector, we have the view direction in blue, and then we have this kind of orange hemisphere of omega that kind of represents all possible incoming directions to our kind of surface point. So this integral comes from the fact that we must kind of consider all those directions. So any of those individual rays in total will kind of be represented by that single unit hemisphere. Now, the issue is there's no analytical solution to this integral, and it can be very tricky to even approximate. So instead, for real-time applications, what we typically do is use analytical light sources instead. And that's where the kind of analytical and their name comes from, that they really help us solve this equation fast and effectively. So with these sources, we can convert that kind of complicated integral to a simple summation over our light sources. Now, in this kind of integral, you have a few different terms here. This term on the right is just that simple impartial and diffuse term. We then have this, which is just the incoming light, which is determined by our light sources. So the real heart of this integral is this function here called the bidirectional reflectance distribution function, or BRDF for short. This is kind of the core of physically based shading, and it determines the ratio of incoming light that gets reflected in the outgoing direction. So that kind of answers that question of, for our surface point, how much of the possible light is going to be reflected towards the viewer. So I can see it written in a few different ways. We write in terms of those three vectors of the view direction, light direction, and then the surface normal. Or I can also write it in terms of the angles between these vectors, shown in this diagram here. So then we can kind of imagine if we took this BRDF and fixed that incoming light direction, and then try to sample the light value with various outgoing directions, we can create this sort of visualization here that shows how much light is going to reflect in different directions given a certain incoming light direction here, given by orange, this orange vector. So we see here, we have this kind of light that goes in all directions, this diffuse lighting by this little hemisphere. But we also have a lot of the lighting being kind of concentrated along the reflection vector of our incoming light. This forms those specular highlights we saw before. This BRDF kind of breaks down into more and more complicated components, the scope of which are just kind of out of the reach for this talk. However, like I said, if you want to learn more, I'll probably be doing a future talk on this, and there is this very detailed tutorial in our documentation. All right. Now, the real kind of power of this physically based shading is the use of texture maps. So material shading allows you to pass a texture map or at least for most of these properties that it takes. So instead of being restricted to having a single value for a property across the entire surface, you can have it vary as quickly as you want using these texture maps. And you can basically imagine, for example, this texture of the base color can be wrapped around our sphere here, and we'll use that for the kind of base color instead of a single solid color like white or red. Now these kind of texture maps allow us to do composite materials and add a lot of fine detail. So here we kind of see this little brick wall texture. We can also do kind of this tiling or even this kind of smudge metallic kind of flooring. So it lets us vary stuff like the base color, the surface normals, metallic coefficient, so how metal the surface is, and other stuff like roughness or sheen and so on. And luckily, these kind of parameters used by material shading are fairly standard across other rendering engines for kind of PBR shaders. So it's very easy to just go online and you can find whole kind of packages of these textures for various materials. So you can pretty much just grab those, plug those into material shading, and start rendering those in Mathematica. And kind of last little note here that's kind of unique to this shader is the ability to do normal maps. So normal maps let us kind of alter the actual surface normal across the object without changing the geometry. So we can kind of approximate very fine details in geometry without the kind of overhead of having more vertices and triangles. All right, so for example, here we have kind of traditional normal map here. It looks a little weird because it's a little purpley, but we can kind of think of it as facing straight on. We have like a blue light shining on it. We have a greenish light shining from above and a reddish light shining from the right side. And that kind of determines how this will look. We can then kind of pass that to material shading and then create this kind of convincing lighting on this plane. So this is just a simple kind of quad. It's only two triangles. Yet as we move the light around, those kind of bumps get shaded in a realistic way based on the direction they're facing. And this is really powerful, especially for small details. I just saw before with that brick texture. Here it is without the kind of base color, so it's only the normals that we're seeing. So here, despite this being a simple sphere with no cracks, as you rotate around, we do get that realistic kind of shadowing of those crevices, which is nice to see and really helps add to the realism at little cost. All right. I think lastly here, we're going to talk about our 2D shaders. So Shaders are not limited to just 3D. You can also use them for 2D graphics. This process tends to be a lot simpler as you don't have to do the complicated projection step or those lighting calculations. However, that rasterization process remains the same. So here's kind of a list of our 2D shaders that are currently available. We have pattern filling and hatch filling, along with this kind of family of gradient shaders. And lastly, we have the new drop shadowing directive. All right, so starting with pattern filling here. So pattern filling draws a texture within the bounds of the object that it's shading. And you can kind of select these pre-existing patterns if you'd like, for example, checkerboard or hexagon tiling, or you can pass in your own image to kind of cover it. So kind of main difference between this and normal texture mapping is that this uses screen space coordinates instead of vertex texture coordinates. So normally when you map a texture to a polygon, you kind of set the coordinates of each of its vertices, where they will land in that texture, and then we just kind of map that to the polygon, just kind of flat on. So if you move the polygon, the texture will move with it. In this case, we can imagine we're kind of taking our texture and laying it across the entire screen. I mean, for example, across this entire kind of orange rectangle, imagine we have this checkerboard pattern. Then as we move our object, the texture stays still, but the object will move as expected. This effect can be really nice for kind of aligning these patterns with multiple shapes. For example, we can have 2 shapes here. They have different sizes, scales, and rotations, yet when they overlap, the textures are seamless still. All right, next up, we have hatch filling. It's very similar to pattern filling that uses those screen space coordinates. So as we kind of move it along, the hatch lines will remain fixed in place relative to the screen. However, the main difference is it does not use a texture, but it actually calculates these lines in the shader itself. We also have control over the kind of thickness and spacing of these lines, as well as the angle that they form. So for example, I can rotate those lines around, I can increase their thickness, or I can increase the gap between them. And all this calculation is done in the shader without any textures. So it can be a little more efficient than the traditional pattern filling. All right, next up is kind of our gradient family of fillings. So these gradients allow you to smoothly transition between colors across the graphics object. So kind of the most basic one here is our linear gradient filling. So here you can see we apply it to this kind of ellipse, and we get this nice smooth transition from blue to yellow to red. Now we have 3 gradient types available as our shaders. We have that linear one, we have radial, and we have conic. They differ in how they kind of determine a pixel's position in terms of that kind of gradient texture. So for linear, it's just a simple from the start to stop of the bounding box of the shape. We kind of just imagine draw a line from 0 to 1, and we evenly space our colors along that line. For radial, we choose a center point, and then the color is based on the distance of the pixel to that center point. And lastly, with conic, we also choose a center point, and then we measure a pixel's rotation around that point, and we use that to determine the angle that we should use to sample from this kind of rotational gradient. We can also change the positions of any of these colors to lie between 0 and 1. For example, here we can move this yellow color a little to the right in both the linear, radial, or conic section, and kind of see the effect of that. I want to see in real time. So here I have an interactive example where I can kind of move the position of the center one, or even swap the colors of these, and we see the resulting kind of effect here. Kind of the last thing about these gradients is they have padding. So when we have our colors, when they don't fill up the full 0 to 1 range, for example, here, it kind of stops right about this section. We need to pad the rest of the shape. So by default, we use this fixed padding where it remains a solid color after the bounds of our gradient. However, we can also do things like periodic, where we repeat that gradient over and over again. It's basically like modulating it. And lastly, we can do reflected, which is where we do that modulation, but for every other kind of example, we will flip it. This way it creates this nice smooth cycle instead of having these hard edges. All right, and last up we have drop shadowing. So drop shadowing is a technique used to simulate 3D depth in a 2D scene. It places a sort of fake shadow behind an object to create the illusion that the object is hovering above the rest of the graphics. So in version 13.1, we've added this new directive drop shadowing that can achieve this effect. For example, here we have a graphics complex of our kind of wolf logo, and we can apply drop shadowing to it, and we see this kind of subtle gray shadow appear behind it. Now, this drop shadowing works on pretty much all graphics objects, from points to lines, to polygons to text. It even includes all of our visualization, such as plot. We can just easily set the plot style drop shadowing to automatically add some nice depth to your plot lines. As far as specifying the shadow goes, you have three kind of settings you can play with. The first here is the offset. So in this diagram, we can imagine the kind of yellow-orange object as being the base object, and this gray one being its shadow. So we can kind of set the offset for which direction the shadow will go and how far it will go. We can also set the blur of the shadow. So when we create that kind of ghost image of the object, we can do image effects on it. In this case, we do blur. As we increase the radius of that blur, the kind of shadow will be more and more kind of blurred out, and we see its reach increase as well. And lastly, we can change the color from the default kind of light gray to any color we want. And just like that, we can have a nice, very flexible kind of drop shadow effect in any of our graphics. We kind of go over some applications for this. So kind of the main one here is adding some extra depth to your objects. So here we have 3 disks. However, we can make it appear as if they're getting increasingly closer to the scene by adding a bigger and bigger kind of shadow behind it. We can also kind of use this as a separator between shapes. Where here, instead of using an edge form, we can kind of add a shadow behind all of our polygons, and it creates a nice depth effect where we can easily distinguish each of these polygons. If we did not use this depth effect, it'd be very hard to kind of tell these apart. For example, if I do this, this is what we get without the drop shadowing. All right. Now, the last one, or second to last one here. So we have glow. We can use a very heavily blurred drop shadow and create this haloing glow effect around our objects. So here we kind of have this magenta glow around this text. And then next we have this kind of outline effect. So in this case, we can use multiple drop shadows on the top, bottom, left, and right of our kind of object, kind of simulate an outline that goes around it. And just kind of lastly for fun, you also kind of animate these drop shadows to kind of create the illusion of our objects kind of jumping off the page and falling back down. All right. And with that, that is the conclusion of my talk. Let me just go ahead and see if there's any questions that have been asked in the chat that I can answer. Let's see. So I have a question saying, hi, cool stuff. Are those shaders similar to GLSL or HLSL? Yeah, so under the hood, we do actually use GLSL for writing these shaders. So we do use that for our shading code. So yes, that is what we use. All right, I'm looking for other questions. I'm not seeing the other ones at the moment that I can answer at this time. So I think with that, I'll go ahead and sign off. So thank you for watching. We'll have another stream coming next Wednesday. And yeah, goodbye.